Hey everyone, ready to dive deep?
Always.
Awesome. Today it's all about neuromorphic computing. We're talking chips that act like, well, brains.
Yeah.
You send over a ton of stuff on this, articles, guides, that Fraunhofer Institute piece, super interesting.
They're doing some amazing work.
Oh, and that hardware guide from Open Neuromorphic definitely helped me wrap my head around the tech.
It's dense but worth it.
For sure. And even built in, they had that explainer, really accessible.
Yeah, they do a great job of breaking things down.
So today, we're going to untangle all that, figure out what's really cool, what matters.
Sounds like a plan.
Okay, so first things first. What is neuromorphic computing? I mean, computers crunching numbers, got it. But how do they start acting like, neurons?
It's a totally different way of thinking about computing. See, traditional computers, they're like assembly lines, right?
Right.
Processing info nice and neat, one step at a time.
Makes sense.
But our brains, chaos.
Yeah.
Interconnected, tons of things happening at once. Neuromorphic computing, it's about capturing that.
So less about straight calculations, more about mimicking how our brains actually work.
Exactly. So instead of one big central processor, you've got these neuromorphic chips. Thousands, even millions of tiny units, all acting like neurons.
Okay, starting to get the picture.
And these neurons, they talk to each other through signals, just like in our brains.
Wow. So why is that such a big deal? Why not just, I don't know, make our regular computers faster?
Well, we're hitting a wall there. Moore's law, about how chips keep getting more powerful.
Right, transistors getting smaller.
Yeah, we're reaching the physical limits of that. Silicon can only get so small.
So this is more than just an upgrade. It's like a whole different path.
Totally. And it comes with some major perks. For one, energy efficiency. Brains, powerful as they are, run on, like a dim light bulb?
Huh, never thought of it that way.
Right. Neuromorphic chips, they use a fraction of the power. Huge for mobile devices, even for, the whole climate change thing.
Makes sense. But there's got to be more to it than just saving energy, right?
Think about what brains do best. Learning, adapting, recognizing patterns.
Stuff computers aren't so great at, yeah.
Exactly. But neuromorphic chips, because they're structured like the brain, they're naturally good at these things.
So this is where AI comes in.
Big time. AI that can learn instantly, adapt to new stuff, make decisions based on complex patterns. More like us.
Okay, so far this all sounds kind of theoretical. Any real-world examples? Are there actually chips out there doing things?
Oh, yeah. Tons of cool stuff happening. You know that IBM TrueNorth chip?
Vaguely?
One of the first big ones? Over 1 million neurons on that thing?
Yeah.
And 250 million synapses.
Seriously? That many?
Mimicking the brain structure, pretty impressive, even compared to some of the newer chips.
And didn't you say it was super energy efficient?
Yeah, just a few milliwatts of power. It's not just talk, it's proof that we can build this stuff, make it work.
So IBM's in the game. Who else is pushing things forward?
Intel's Luigi chip is doing some really interesting stuff.
Yeah.
Even more efficient, and get this, it's got on-chip learning built in.
On-chip learning? What does that even mean?
So most AI systems, they learn by sending data back and forth to the main processor.
Right.
But Low-E, it's got the learning built right into the chip itself. It adapts, modifies its connections on the fly.
Wow.
Like it's constantly rewiring itself based on what it encounters.
That sounds incredibly powerful.
It is. Opens up all sorts of doors for adaptable AI. They're using it for things like odor recognition.
Wait, a computer that can smell?
Yeah, crazy. Right. And for controlling robots so they can learn and adjust in real time.
Okay, I'm definitely getting the this is a big deal vibe.
Definitely. But like anything, there are challenges. We're still early days here.
Right, makes sense.
Scalability is a big one. Our brains, billions of neurons. Getting chips to that level of complexity is tough.
Yeah, can't just copy and paste a brain onto a chip, I guess.
And even if we could, programming these things is a whole other beast. Traditional code, not going to cut it. Need languages that can handle massive parallelism, that event-driven architecture.
So new hardware, A&D, new software, a whole new way of thinking about computing.
You got it. That's what makes it so exciting. It's not just better computers. It's reinventing how we process information.
Okay, gotta ask.
Yeah.
Are there any, big collaborations, projects going on to tackle these challenges, I mean?
Oh, absolutely. The Spinnaker project. That's a fascinating one. Not just a chip, it's a whole system. They simulate huge spiking neural networks. Think of it like a network of thousands of mini brains all working together.
Instead of one giant brain on a chip, they're going for a more distributed approach.
Exactly. It lets them simulate crazy complex neural networks almost as complex as the human brain itself.
What can you even deal with that kind of power?
Neuroscientists are using it to model brain activity, study disorders, even explore consciousness.
So we're building artificial brains to understand our own brains. Meta.
It is. And it's helping us develop new AI algorithms, potentially leading to even more intelligent systems down the road.
This is blowing my mind.
It's a lot to take in.
It is. Sounds like we've only scratched the surface here.
Oh, yeah, there's so much more to unpack.
Well, can't wait to dig deeper.
It too.
So much more to unpack indeed. Before the break, IBM, Intel, they're big players, but I get the feeling there's a whole ecosystem out there.
Oh, yeah. Tons of companies pushing the boundaries. Sense, for example, they've got these chips, Spec and Xylo, designed for ultra-low power.
Spec and Xylo, those names sound like something out of a futuristic video game.
Right. Catchy, for sure. But the tech is serious. They're both event-driven, like we talked about, but each one's kind of specialized.
Okay, so what, like Spec does one thing, Xylo another?
Kinda. Spec is all about visual processing. Imagine a tiny camera, super energy efficient, that can recognize objects, track movement, all on a tiny power budget.
Like an artificial eye, basically.
Yeah,
Could fit on a tiny robot or a drone.
exactly. Then you've got Xylo, more of a general-purpose chip, but still super efficient. Perfect for what they call edge computing.
Edge computing, that's where things get interesting for the Internet of Things, right?
Big time. Instead of sending all that data to the cloud to get processed, you do it right there on the device. Faster, less lag, more private, too.
Data stays put. I like that.
Makes sense for a lot of applications.
Okay, so we've got these tiny, powerful, efficient chips. What else is out there on the cutting edge?
Well, material science is a huge part of this. Silicon, it's been the workhorse, but we're kind of reaching its limits.
So what, are we talking about some exotic new stuff? Unobtainium?
Some of it sounds pretty sci-fi, yeah. Memristors, for example. It's basically a resistor, but it's got memory, like it remembers its previous state. Kind of like synapses in the brain. It lets them learn and adapt in a way that normal transistors can't.
So it's not just the structure of the brain we're copying, it's like the way the individual parts actually work.
You got it. Then there's carbon nanotubes. Super tiny tubes of carbon, incredible electrical properties. Could lead to transistors way smaller, way more efficient than anything we can do with silicon.
Okay, my brain needs a minute to catch up. How do these new materials actually translate into better neuromorphic chips?
Think of it this way. Smaller transistors, less power hungry, means we can cram more of them onto a chip. More neurons, more connections, more power overall.
So we're not just talking about small improvements here and there. This could be a major leap.
It really could. And it's not just raw power. These new materials could lead to chips that are more flexible, tougher, even biocompatible.
Hold up, biocompatible, like merging electronics with biology.
And it's still early, but yeah, that's the idea.
Yeah.
Imagine chips that can interface directly with the nervous system.
Oh.
Could be used to restore lost function, maybe even enhance what we can already do.
Okay, yeah, that's pretty mind-blowing. Let's zoom out for a second, big picture. We've talked chips, materials, but what are the big trends in neuromorphic computing overall?
One of the biggest is the shift away from Moore's law as the only path forward. Shrinking transistors has gotten us this far, but we need new approaches. Neuromorphic computing is about efficiency, doing more with less, using parallelism. It's about smarter, not just faster.
It's a whole different philosophy.
It really is. We're moving away from that one central processor doing everything. It's more about distributing the intelligence throughout the system.
Kind of like the brain, right? Different areas specialize for different things.
Exactly. That's huge for robotics, for the Internet of Things, where you need things to make decisions on their own, adapt.
Less computer brains, more computer nervous systems.
Love that analogy.
Yeah.
Another trend is this idea of event-driven computing. Normal systems, the processor's always running, even when it's not really doing anything useful.
Wasting energy.
Exactly. Event-driven, things only happen when there's something to process, just like the brain. Way more efficient.
Okay, so that's how we get these chips that can run for weeks on a single charge.
Yep, sensors that can monitor your health 24/7, robots exploring who knows what for months, spacecraft that can go further than ever before.
The possibilities are pretty incredible.
And it's all inspired by the most efficient computing machine we know, our own brains.
It's more than just a new tech. It's a whole new way of thinking about how we interact with technology.
Couldn't said it better myself.
Yeah.
It's a real paradigm shift. Huge implications for the future.
Okay, I'm definitely eager to hear about those implications. But before we get ahead of ourselves, what about right now? What are some of the real-world applications of neuromorphic computing that are already happening?
One area where it's already making a big difference is sensory processing. Cameras, microphones, touch sensors, all that stuff.
Right, all about interpreting data from the world.
And neuromorphic systems, they're perfect for that. They can process that information in real time, just like our brains.
So smarter cameras that can, I don't know, recognize faces, track objects, microphones that can filter out noise.
Exactly. And it goes beyond that. Radar, LiDAR, medical imaging, they can handle it all.
Wow, the applications seem endless.
They really do. In medicine, for example, there's a lot of excitement about using these systems to analyze medical images, X-rays, MRIs, help doctors spot things they might miss.
So instead of just a doctor looking at a scan, you've got AI that's specifically trained to find, I don't know, tumors, other problems.
That's the idea.
Yeah.
And because these systems are so fast, so efficient, you can even use them for real-time diagnosis, monitoring.
Could be a game changer, especially in emergencies.
Absolutely. And it's not just medicine. Robotics is another huge area. These chips can control robots in a much more sophisticated way, more natural movement, adapting to changes, even learning new skills.
So less like robots that just follow a set of pre-programmed instructions, more like robots that can figure things out on the fly.
You got it. Important for robots working in messy environments like factories, hospitals, even our homes eventually.
It's like we're moving from robots as machines to robots as like partners.
I like that. Working with us, not just for us.
And neuromorphic computing is key to making that happen.
Big time. Smarter robots, but also safer, easier to work with.
That's good to hear. I know some people get a little freaked out about robots getting too smart.
I get it. But it's about designing them the right way. Neuromorphic computing, with its focus on efficiency, adaptation, learning, it's a good path forward.
Definitely a lot to consider.
For sure. What about other industries? Oh, pattern recognition and anomaly detection, that's a big one.
Anomaly detection, so like finding things that are out of place.
Exactly. Fraudulent transactions, cyber attacks, even subtle changes in someone's health, that could be an early warning sign.
Okay, yeah, that makes sense.
And because they're so efficient, they can do this in real time. A security system that spots a problem instantly, a medical device that alerts you to something before you even feel sick.
Neuromorphic computing could literally be saving lives.
It very well could. And as the tech keeps improving, who knows what other applications will pop up? Personalized medicine, drug discovery, climate modeling, the list goes on.
It's pretty amazing stuff.
It really is. More than just a new type of chip, it's a whole new way of thinking about technology. A real paradigm shift.
And one that's going to have a huge impact on our world.
Without a doubt. It's a really exciting time to be following this field.
I'm definitely feeling that excitement. Ready to take one last leap into the future of neuromorphic computing.
Let's do it.
Okay, so much to think about. We've talked about the amazing potential, but with any powerful tech, there are always those, bigger questions.
Oh, absolutely. And with neuromorphic computing, some of those questions get pretty deep.
For sure. Like one that comes to mind is control. As these systems get more and more advanced, learning on their own, adapting, how do we make sure they stay, well, on our side?
It's a crucial question. The idea of an AI going rogue, it's a classic sci-fi trope, right?
Right. But is it a realistic concern, or is that just Hollywood being dramatic?
It's definitely something we need to think about. One approach is to design these systems from the ground up with ethics in mind. Build in safety mechanisms, anticipate potential risks, that kind of thing.
So like putting guardrails on the development to keep things from going off track?
Exactly. And it's not just about preventing bad stuff from happening. It's also about making sure this tech is used for good, for the benefit of humanity,
Right, making sure we're steering this ship in the right direction from the start.
Exactly. The earlier we have these conversations, the better.
Okay, so control, ethical considerations, those are big ones. But what about like the broader picture? How do you see neuromorphic computing changing the world in the long run?
One of those fascinating possibilities is this idea of blurring the lines between humans and machines. Imagine being able to integrate neuromorphic devices directly with our brains.
Whoa, wait. Brain-machine interfaces. Are we talking full-on cyborg stuff?
It's not as sci-fi as it sounds. Researchers are already working on devices that can record brain activity, even stimulate specific areas. And as neuromorphic tech gets better, those devices will get more powerful, more sophisticated.
So what, like using our thoughts to control things, enhancing our abilities?
Potentially, yeah. Could revolutionize medical treatments, help people with disabilities, maybe even lead to entirely new ways of communicating, interacting.
It's incredible to think about, but also Kind of scary. Like, what does it even mean to be human if we're merging our minds with machines?
That's a big question. Raises all sorts of philosophical issues about consciousness, identity, even the definition of life itself.
Yeah.
Definitely something we need to discuss as a society.
Okay, last question before we wrap things up. If you had to look into the future, what do you think the ultimate impact of neuromorphic computing will be?
I think it has the potential to completely change how we interact with technology. Right now, it's all keyboards, screens, voice commands. But imagine a world where we can interface with tech in a way that's more natural, more intuitive, using our thoughts, emotions, maybe even our subconscious.
So instead of typing or swiping, we're literally thinking our commands.
It might sound crazy, but it could be the future. And it's a future that's being built right now by researchers, engineers, dreamers all over the world.
It's a future I'm definitely excited to see unfold. Well, that brings us to the end of our deep dive into neuromorphic computing. From the science behind these incredible chips to the potential impact on humanity, it's been quite a journey.
It really has. And we've only just scratched the surface. There's so much more to learn, to explore, to discover.
Absolutely. So to everyone listening, keep that curiosity alive, keep asking questions, keep pushing the boundaries of what's possible.
And most importantly, keep an open mind. The future of technology, it's full of surprises, and neuromorphic computing, it's just one piece of the puzzle.
Well said. Until next time, keep diving deep.
Happy diving!